Good afternoon, everyone. So as this is the final day and also the final session of this long conference, and I think everyone's energy and enthusiasm are in the ground level, so I don't want to bore you much. Okay, so anyway, at first I want to thank the organizers for giving me this great opportunity to present my work in this platform. And today I'll be talking about probing non-minimal coupling through superhorizon instability and secondary gravitational waves. And I have recently finished this work in collaboration with Professor Debaprasad Maiti and Subhashish Maiti, and both of them have already presented here. Okay, so let us start. So this is the overview of my talk. At first I'll tell you the main motivation of this study, and then I will discuss all these points one by one, and finally I'll conclude my talk giving a brief outline to the main outcomes of this study. Okay, so the motivation is a scalar field non-minimally coupled to gravity can be treated as a potential source of secondary gravitational wave. And these scalar fluctuations, because of its non-minimal coupling to gravity, experience a significant long wavelength or higher instability beyond a certain coupling strength. And this being a possible source of gravitational wave is expected to leave a visible imprint on GW spectrum also, which can be probed by various future GW observatories. And finally, our goal is to constrain this non-minimal coupling strength based on current Planck bound on tensor to scalar ratio and delta N effective. Okay. So these two plots are actually representing the cosmic evolution and the evolution of the co-moving Hubble horizon. And the left panel of this figure is representing various evolutionary phases of the early universe. And earliest of them is the inflation. So in this work, I shall mainly concentrate on this early era, the inflation and the post-inflationary phases. And right panel of this figure is representing the time evolution of the co-moving Hubble horizon. During inflation, there is a shrinking Hubble radius, and after that, it will grow over time. So different modes of these fluctuations which left the horizon at different times during inflation will progressively re-enter the horizon either during reheating or at different points of time at some later phases. And these long wavelength modes will actually experience this super horizon instability caused by the non-minimal coupling to gravity. And that's why those long wavelength modes are going to be extremely important in the present study. Okay. So before going to talk about the instability dynamics, I shall just briefly tell you the importance of reheating phase. So at the end of early accelerated phase of expansion, universe was left in a state of super cold state of vanishing number density and vanishing entropy density. So there is a huge time and energy gap between the end of inflation and the Big Bang nucleosynthesis. So to fill up that gap, there must be a phase where universe must transit to a state of hot thermal and radiation dominated phase. So this phase is basically known as the reheating phase. So in this phase, what happens? The classical homogeneous inflated background decays into all kinds of standard model and beyond standard model particles, and this eventually gives rise to a hot thermal bath, and finally reheating concludes. So these two figures are actually given to have a better visualization of this reheating phase. So this is basically the potential model, and the flat surface of the potential is actually representing the inflation phase, where inflaton field is slowly rolling over the flat surface, and there is a natural consequence at the end of this rolling. The inflaton field will start oscillating around the zero minimum of the potential, and this is basically the commencement of the post-inflationary reheating phase. So I will not go into the detail of this phase. Okay. So now I shall give you a brief account to the general construction of a scalar field non-minimally coupled to gravity. So this is the general form of the Lagrangian of the system. The first part is the Lagrangian of the inflaton field, where V phi is nothing but the some generic form of the inflaton potential, and the second part is representing the Lagrangian of the scalar field, where xi chi square is nothing but the non-minimal coupling to gravity. R is the Ricci scalar, A is the scale factor, and xi is the non-minimal coupling strength. So Fourier decomposing this scalar field, we finally have the evolutionary equation of the each field mode, I mean the each Fourier mode of the scalar field, and which is given by this, where the Ricci scalar can also be expressed in terms of the scale factor like this. Okay. So now I shall talk about the appearance of instability in the system. So this is the general form of the scale factor, where omega phi is the equation of state parameter, and varying this equation of state parameter from 0 to 1, we can have the different evolutionary form of the scale factor in the post-inflationary phase, and substituting omega phi equal to -1, we can have the de Sitter-like evolution during the inflation phase from this particular form of the scale factor. So in this work, I shall mainly concentrate on the higher modes or the long wavelength modes and very low mass case of the scalar field. And subject to this particular form of the scale factor, we have the inflationary and the post-inflationary evolution of the each field mode, which is given by these two expressions. So here one important point is the appearance of instability in the system. So when this frequency term, that means omega square, becomes negative, so there is an instability, and this is known as the tachyonic instability. And in the inflationary evolution, we see that when xi, that means the coupling strength less than 1/6, so this instability situation arises. Whereas in the post-inflationary phase, depending upon the equation of state parameter, this situation alters. When omega phi greater than 1/3, xi greater than 1/6, and when omega phi less than 1/3, xi less than 1/6 will be responsible for the appearance of instability in the system. So there is a constant interplay between these two parameters, omega phi and xi, by which the appearance of instability in the system is decided. And it would be, this particular feature would be extremely interesting while studying the dynamics of the scalar field, what we shall see soon as I proceed along. Okay. So now cosmological spacetime has an appealing property to be adiabatically flat in the asymptotic past and future. So employing that idea, we can compute the adiabatic vacuum solution in the inflationary as well as the post-inflationary phase, which are given by these two expressions. And where nu1, nu2 and mu are some indices function of omega phi and xi, and when eta bar is some Driscoll time variable. And now introducing the Bogoliubov coefficients alpha k and beta k, we can have the general reheating field solution as a linear combination of the adiabatic vacuum solution, which is given by these two. So in the subsequent discussion, we shall mainly study the instability dynamics of this general reheating field solution, and that's why this is important. Okay, so these two figures are actually representing the time evolution of the scalar field amplitude for two different equation of state and for a given coupling strength xi. And in the left panel, we see for omega phi equal to 0, there is no instability at all present in the system. And no matter how long the wavelength is, but they will not experience any instability, even though the coupling strength is high. Whereas in the right panel, we see that for omega phi equal to half, there is a prominent instability present in the system. And we see because of the prominent instability, there is a significant enhancement of the field amplitude. And interestingly, we find that the longer the wavelength, the stronger the instability and the higher the enhanced field amplitude. Okay. So now two important quantities that we shall define, that is the field power spectrum and the field energy density spectrum, which is given by these two expressions. And using the field solution, we have this spectral behavior of the energy density spectrum for three different regimes of the coupling strength. And as I have already shown that this instability effect is actually important for the higher equation of state. So from now on, I shall mainly concentrate on the higher equation of state, that is omega phi greater than 1/3. Okay. So these two figures are actually representing the energy density spectral behavior for two different equation of state and for different values of xi. And for omega phi equal to 0, we see that for xi equal to 0, there is a heavily red tilted energy density spectrum. And if we keep on increasing the coupling strength at a particular point, there will be spectral will be completely scale invariant. And if we further increase the coupling strength, the spectral will remain blue tilted, but having a slight variation of the amplitude as obvious in this figure. And for omega phi equal to half, we see that for xi equal to 0, unlike the previous case, there is a slightly blue tilted spectrum, and if we keep on increasing, the spectrum will remain blue tilted having a slight variation, and at a particular point that is xi critical, the spectral behavior will be completely scale invariant, and with the further increase, it will remain red tilted. So these interesting features of the energy density spectrum will actually affect the gravitational wave spectrum in the subsequent study. Okay. So now before going to talk about the gravitational wave, I shall just briefly tell you the model admitted prediction of reheating parameters. So in this work, I shall not consider any specific reheating dynamics. I will consider a generic reheating scenario where reheating temperature will be a free parameter, and varying that parameter, we can generate different parameters of reheating. So these are all standard definitions. I will not talk about these things in detail. Okay. So now this is the general construction of a secondary gravitational wave. This is the part of detectable metric where Hij is the tensor perturbation satisfying the transverse stressless property, and one important quantity here is the anisotropic stress tensor, which is a function of the scalar field chi. So this is basically the source field, and the minute details of the dynamics of the source field will enter into the system of gravitational wave through this particular term. And this is the evolution equation of the tensor field mode, where PLM is nothing but the transverse stressless projector. Okay, so now solving the previous evolutionary equation of the tensor field mode, we get such kind of behavior of the spectral behavior of the primary as well as the secondary gravitational waves, where primary gravitational wave spectral behavior are very standard. For the mode scale less than KRE, there is perfectly scale invariant behavior, and for k greater than KRE, there is a non-trivial index that is in omega phi, which is a function of equation of state. But in this particular scenario, for secondary gravitational wave, for the mode scale less than KRE, we'll have a non-trivial spectral index, and interestingly find that this spectral index is exactly twice the spectral index of the energy density spectrum of the scalar field that I showed earlier. Okay. So now this is the behavior of the total gravitational wave spectrum combining the primary and the secondary. So and for three different parameters, coupling strength, reheating temperature, and the inflationary energy scale. So in all three plots, we see that the one common feature is that at low and intermediate frequency ranges, the SGW strength is overcoming the PGW1, and not only that, the enhanced SGW spectrum is actually passing through various future GW observatories like LISA, BBO, DECIGO, and some part of ET also. So if we consider the first figure, we see there is a with the increase of reheating temperature, there is a gradual decrement of the strength. This is because of with the increase of reheating temperature, as we are getting narrower and narrower reheating span. That means smaller and smaller NRE. That means because of the gradual decrement of the, because of the absence of the prolonged instability of the source field, this is this SGW strength is gradually decaying. And also for the second figure, with the increase of the coupling strength as the prolonged instability is growing of the source field, so this basically causes the gradual enhancement of the SGW strength. Okay, so now I shall come to the one of the most important part of this study, that means constraining coupling strength Xi through different observational bound, that means tensor to scalar ratio and delta N effective. So for omega phi greater than 1/3, we have this expression of tensor to scalar ratio. And this is the particular index. So as we have a upper bound of the tensor to scalar ratio at the CMB scale, so this automatically imposes a upper bound on the coupling strength Xi. And another important constraint on the coupling strength will come from the delta N effective. So as we are not considering this massless scalar as a dominant radiation component during the reheating phase, so it may contribute to the total radiation energy at the time of CMB decoupling. So it may be considered as a possible candidate for dark radiation. So if this dark radiation component solely contributes to delta N effective, then that situation can be expressed by this expression. So now combining these two bounds, we finally have the parameter space Xi max versus for different omega equation of state for different reheating temperatures, which is given by this plot, where the dotted lines are the bounds obtained from delta N effective, where solid lines are the bound obtained from tensor to scalar ratio. So now another important bound, that is the delta N effective, where the gravitational wave is actually contributing to this delta N effective bound. So if we now consider the total contribution of gravitational wave is coming from delta N effective is coming from gravitational wave, then that situation can be expressed by this expression, and this expression can also be translated into the lower bound of reheating temperature. And this temperature is important because if we choose any reheating temperature below that this limit, then that will actually be forbidden because of the overproduction of the primary gravitational wave, which will be anyway inadmissible from the perspective of BBN bound. So now combining all these three bounds, we finally have this parameter space Xi max versus TRE for three different equations of 3/5, 2/3, and 5/7, where three red vertical lines are actually representing this lower reheating temperature bound, below which, because of the overproduction of primary gravitational wave, this is completely forbidden. And another three colored vertical lines, cyan, blue, and magenta, representing a particular reheating temperature associated with this equation of state, below which we will get the stronger bound from the delta N effective, and above which we will get the stronger bound from tensor to scalar ratio. Okay, so now I will summarize my talk. So post-implicit instability effect is dominant for higher equation of state, and the longer the wavelength, the more the enhancement owing to prolonged instability for a larger coupling strength Xi. And another important point is for the higher equation of state, omega phi greater than 1/3, significant higher instability beyond a certain Xi leaves a visible amplitude on GW spectrum, and which is actually overcoming the PGW strength at low and intermediate frequency regimes. And finally, we can constrain this coupling strength on the basis of these two observational bound. And we find that for any higher equation of state, omega phi greater than half, we get the maximum bound on Xi, that is less than equal to 4, satisfying these two observational bounds. And for the lower equation of state, unlike omega phi greater than 1/3, we put a lower bound on Xi. And for example, I can mention the value that for omega phi equal to half, omega phi equal to 0, we get a lower bound on Xi, that is Xi minima should be greater than equal to 0.02, actually subject to that two observational bounds. Okay, so thank you for your attention.
Thanks for the nice talk. Okay. So questions?
Nice to see for all possible W equation of states.
Yeah.
What are the all possible bounds on Xi?
Okay, so here I have mentioned that for any equation of state, omega phi greater than half, subject to these given bounds, will always have a maximum possibility of Xi that is equal to 4. It should be less than that to satisfy those given bounds. For higher equation of state.
But
I'm
that's
talking
for
about.
higher, right?
That is for higher
Yeah, so
equation
if
of
you
state.
draw
But
2D parameter space,
yeah,
there you can color code Xi
yeah.
for the whole possible range of.
Actually, depending upon the nature of the, the energy density spectrum of the source field, for omega phi less than 1/3 and omega phi greater than 1/3, there will be a behavioral difference, and that actually affects the final bound for higher case and for the lower case. For lower, we will get the lower bound, and for higher, we will get the upper bound.
So maybe I'll talk to you later.
Yeah, of course.
Any other quick question? Okay, if not, thank you.
Thank you.
And